In this video, I want to show you different methods for finding limit of sequences. We will see different type of examples. Sequences with trigonometric expressions, sequences with inverse trigonometric expressions, sequences with exponential and logarithmic functions, sequences involving factorial. And for finding the limit of sequences, we will learn different techniques like L'Hopital, sandwich or squeeze theorem, and other techniques. So let us start. The first example is 5n over n to the 2 plus 9. For finding limit of this sequence, I will show you 4 different methods. Some of these methods are fast and easy. Some of these methods are more general and you can apply them for other examples. The first method that I want to show you for finding limit of this sequence is very effective and very fast method that you can find limit of rational expressions like this example really very fast. In this method, for finding limit of the sequence, you know that when we talk about limit of a sequence, we want to find limit of the sequence at infinity. So here we want to find limit of 5n over n to the 2 plus 9 as n approaches infinity. In this method, we keep the dominant term in numerator and the dominant term in denominator. What is a dominant term? The term with the highest degree. The term that is significantly bigger than the other terms. So we ignore, we delete, we cancel other terms. Just we keep the dominant term or terms that are dominant in numerator or in denominator. Look at the numerator. We have only one term, so we have 5n. In denominator, we have 2 terms, n to the 2 and 9. Which one between these 2 terms is significant? Which one is more important? Which one is bigger? N to the 2. Because n to the 2, n approaches infinity, but 9 is a constant, so n to the 2 is important. We keep this and we ignore 9 completely. Now simplify this. 5n over n to the 2 is 5 over n. So we have a limit of 5 over n as n approaches infinity. We know that limit of a number, in numerator we have a number, over something that approaches infinity is 0. Any number over infinity approaches 0. So the limit of this sequence is 0. So this given sequence approaches 0. So this sequence is a convergent sequence and it converges 0. So this is our first method for finding the limit of this sequence. Keep the dominant terms, the terms that are bigger, significantly bigger than the other terms. Basically, the dominant term is a term that the other terms that we ignore them are nothing compared to the dominant term. For that reason, we can ignore those terms and we can just keep the dominant term. Now let me show you another method for finding this limit. The second method for finding this limit is using L'Hopital rule. Remember, we can use L'Hopital rule, which was a method for finding limits of functions. We can use L'Hopital rule in 2 cases. When we have a limit in the form of 0 over 0 or infinity over infinity. Usually in sequences, we have infinity over infinity. So we can use L'Hopital rule for finding limit of sequences. But attention, don't make this mistake to write limit n approaches infinity and write the expression. No. When you want to use L'Hopital rule, make the variable, change the variable name from n to x. So basically you have to write it this way. For finding limit of this sequence, we are going to find limit of 5x over x to the 2 plus 9 as x approaches infinity. Yes, this is just a change in the name of the variable. Maybe you think by yourself, what is the difference? This is the same thing. The thing is that when n is integer, in the sequence, n is an integer. N cannot be decimal, n is an integer. And when the variable is integer, you cannot take derivative from that. Mathematically, it's wrong, completely wrong, to take derivative of something like 5n or n to the 2. So to write your solution in the right way, change the variable name. It's very simple. Change the variable name to x, then start using L'Hopital rule. Based on L'Hopital rule, if you remember, for finding a limit which is in the form of infinity over infinity, we take derivative of numerator. What is the derivative of numerator? 5. What is the derivative of denominator? 2x. Because the derivative of x to the 2 is 2x. And the derivative of a constant like 9 is 0. So the derivative of numerator is 5. The derivative of denominator is 2x as x approaches infinity. And now if you pay attention, 5 over infinity, a constant over something that approaches infinity is 0. So these two answers are of course the same. So L'Hopital rule is another way for finding limit of sequences. Of course, if it is possible, and it is possible when we have infinity over infinity, then we can use L'Hopital rule for finding the limit of the given sequence. And of course, we use L'Hopital rule when finding derivative is not too complicated. If finding derivative of numerator or denominator is impossible or very challenging, maybe it's better to ignore using L'Hopital rule. For example, suppose in the denominator you have factorial. Can we take derivative of factorial? No. So we cannot apply L'Hopital rule for such examples. We need to have fraction first of all, and we need to be able to find derivative, like this example. Now let me show you another method for finding limit of this sequence. So this is the third method for finding limit of this sequence. If you remember limit of functions at infinity, for finding limit of functions at infinity that are in the rational form, so suppose we have an expression in numerator, an expression in denominator. For finding these type of limits, if you remember from functions, we divide numerator and denominator, every term of numerator and every term of denominator by the highest degree of denominator. This was the method for limit of functions at infinity, if you remember. Divide every term of numerator and every term of denominator by highest degree of denominator. So here, if we want to apply this method here, for finding this limit of 5n over n to the 2 plus 9, we have to look at the denominator. And as you can see, the highest degree of denominator is n to the 2. So we divide every term of numerator and every term of denominator by n to the 2. Like this. Now we start simplifying these expressions if it is possible. In numerator we have 5n over n to the 2. So if we simplify that, we have 5 over n. In denominator, n to the 2 over n to the 2 is 1 plus 9 over n to the 2 is 9 over n to the 2. We cannot do anything with that. Now attention, because n approaches infinity, the limit of 5 over n is 0, because a number over infinity is 0. So the limit of this part is also 0. So this limit is equal to 0 over 1 plus 0. So 0 over 1 plus 0. And this equals to 0. So the limit of this expression is equal to 0. As we can see, all of these answers in 3 different methods are the same. They should be the same. This is another way that you can find the limit of this sequence. Now, let me show you a 4th method. Maybe you wonder by yourself, you ask by yourself, why we have to learn different methods? Because some of these methods work better in some situations, in some examples. So learn different techniques and start applying them when they work effectively. Of course, this technique is very effective and compared to this method is faster. But attention, in this method you show your work, but here basically this is not really mathematical way. It works, you can get the answer, But maybe this is not a completely mathematical method. Which we say in this method, what we say? We say just keep the dominant terms and ignore this term. And as you can see here, also at the end we ignore this because it becomes at the end 0. But here we do it in a faster way. And now let's talk about the fourth method. In the fourth method, I want to remind you something again from limit of functions. So let me rewrite the given sequence here. The sequence was this 5n over n to the 2 plus 9. But before that, let me remind you something from limit of functions at infinity. If you remember, when we had polynomial, any polynomial like x to the 2 minus 4x plus 3 over another polynomial, a rational expression basically, if you remember this from functions. So whenever we have a rational expression like this expression, for finding the limit of the rational expression, we had this rule that if the degree of the polynomial numerator is bigger than the degree of the denominator, then the limit is either positive or negative infinity or negative infinity. If the degree is the same between numerator and denominator, then the degree would be a number, which that number is the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. I will explain this in a moment. Let me finish this, then I will explain this in detail to you. At the end, if the degree of numerator is less than the degree of denominator, then the limit is 0. In our example here, if we want to use this technique, look at the numerator, 5n. Look at the denominator, n to the 2 plus 9. The degree of numerator is 1. In denominator, we have degree 2. So the degree of the denominator is bigger than numerator, or the degree of numerator is less than the degree of denominator. And when this happens, the limit of the sequence is, limit of the function and limit of the sequence is 0. So by this technique, you do basically nothing. Just you need to remember this, and if you remember this, you can find the limit of the rational expression right away. So the limit is 0 because the degree of numerator is less than the degree of denominator. Let me show you some examples of the other cases and how we can use this technique to find limit of sequences really easily. For example, suppose we have this. an is given n to the 2 minus 4n plus 7 divided by 5n to the 2 plus n plus 10. Based on this, what is the limit of this sequence? What is the limit of an? Let me name this bn. So what is the limit of bn when n approaches infinity? Degree of numerator is 2. Degree of denominator is 2. So this is this case. So now look at the leading coefficient. What is coefficient of n to the 2 here? 1. What is coefficient of n to the 2 here? 5. So a is 1, b is 5. So the limit of this sequence is 1 over 5. And again, you can find limit of this sequence with the other methods that I have shown you so far. Method 1, method 2, method 3. Using L'Hopital, using keeping the dominant term, using dividing the numerator and denominator by highest degree. You can use those methods, but this method is faster, at least for these examples. Let me show you an example from this case basically. For this case, consider this sequence. Cn, consider the sequence Cn given by, for example, 5n to the 3 plus n plus 1 over 2n plus 5, for example. What is the limit of this sequence? When n approaches this infinity, the limit of this sequence is infinity. Why it is positive infinity? How we can figure out is it positive infinity or negative infinity? First of all, we note that the degree of numerator is bigger than the denominator, so it's obvious that the answer is infinity. But it can be positive or negative infinity. To figure out that, focus on these two terms because these are important. These are nothing compared to these two. Now look at the coefficients. The coefficient of the top is positive. Coefficient of this one is positive. So positive over positive is positive. But let's say this example was negative 5n to the 3. Then the limit of this sequence would be negative infinity. Because negative 5 divided by 2 would be negative at the end. So the limit is negative infinity. Now let's say, what about if we had a negative also here? Then when we consider these two, when we divide negative 5 by negative 2, negative with negative cancel, this would be positive. So depending to the sign of this number and sign of the leading coefficient, these are leading coefficients, depending on these two, we can figure out is it infinity or negative infinity. So this is the fourth method for finding limit of a sequence when it is like a rational expressions. Now look at these examples. These two examples are also in the rational expression form. So we can use this last technique, the fourth method, for finding limit of these sequences right away without thinking. For example, what is the limit of this sequence when n approaches infinity? The limit of this sequence when n approaches infinity is 2, because degree of numerator is the same as degree of denominator. When the degrees are the same, the limit is the ratio of these coefficients, 2 over 1, so the limit is 2. You can use other methods. You can use L'Hopital rule to find limit of this, but you have to apply L'Hopital rule 3 times to find this answer. You can divide every term of the top, every term of the bottom by highest degree of the bottom, which is n to the 3. Then you can find the limit. This is another way. You can use the first method that I taught you in this video. What was that method? Ignore smaller terms. Keep these two. 2n to the 3 over n to the 3 is the same answer 2. So this method is also very effective, as you can see. So the limit of this sequence is 2. Look at the next example. The degree of numerator is bigger than the degree of denominator. So the limit of this sequence should be infinity. But is it infinity or negative infinity? What do you think? Limit of this sequence when n approaches infinity is negative infinity. And the reason is that this coefficient is negative, this coefficient is positive, negative over positive is negative. So the limit is negative infinity because the degree of numerator is bigger than the denominator, and the coefficients gives you a negative. You can use L'Hopital rule to find this limit. You can use other methods, like dividing numerator and denominator by highest degree of denominator, which is n. So you can divide every term in numerator and every term in denominator by n. It takes some algebra to do the question and simplify and get the answer, but it works. And if you use first method that we learned in this video, what was the first method again? Keep the dominant term. What is the dominant term in numerator? This term. What is the dominant term in denominator? 4n. Let me show you how it works for this question. Suppose we want to find the limit of this sequence. So we want to find limit of this sequence with the first method. In the first method, if you remember, we just keep the dominant terms, the terms with the highest degree. So this over this. Simplify this a little. N to the 2 with n cancels and we have negative 3n over 4. N approaches infinity. Now n goes to infinity. So this n goes to infinity and we multiply this infinity by a negative 3/4. Because of this negative, the answer would be negative infinity. When you multiply a number that is positive by infinity, it's positive infinity. But if you multiply positive infinity by a negative number, the answer would be negative infinity. So The answer is the same, as you can see. Now look at these two examples here. 2 radical n over radical n plus 3, n to the 2 over radical n to the 3 plus 4n. These are not really rational expressions, because maybe you think by yourself you have a radical. Yes, you are right. But attention, again we have n with different powers in numerator and denominator, so we can consider them as rational functions. Basically, if you think for a moment, you can write this as 2n to the power of 1/2 over n to the power of 1/2 plus 3. So if you think this way, you can still use the methods that you have learned so far for finding limit of this sequence. If we want to use the fourth method, which was the fourth method? The method which was based on the degrees. What is the degree of numerator? N to the 1/2. The degree of denominator is also n to the 1/2. So the limit of this sequence based on that method is the ratio of the coefficients. So the limit of this sequence, limit n approaches infinity of this sequence, is equal to leading coefficient over leading coefficient, 2 over 1 or 2. This is one way, which is based on the fourth method. The other method that we can use for finding limit of this sequence is the first method. What was the first method? Keep the dominant term. What is the dominant term in the top? Just we have one term, so whatever it is dominant. But in the bottom, radical n is important. We ignore 3. N approaches infinity. Simplify this with this, 2. Same answer. Also, you can use L'Hopital rule to find this limit, but you have to take derivative. So these methods are easier compared to L'Hopital. Another way is to divide numerator and denominator by highest degree of denominator. Let me show you that method as well, very fast here. Limit n approaches infinity, so we divide every term in the top and every term in the bottom by radical n, because radical n is the most important term in denominator. So we divide every term in numerator and every term in denominator by highest degree of denominator. So we have this. What is this? 2. What is this? 1. What about this? 3 over radical n when n approaches infinity is 0, because any number over infinity is 0. So we have 2 over 1. 2. The answer is the same. Now look at the next example. What about this? If you pay attention, the degree of numerator is 2, n to the 2. What is the degree of denominator? What is the highest term, highest degree of the denominator? If you pay attention, this is like nothing compared to this. So here, basically, the highest degree of denominator is n to the 3 over 2. Don't make this mistake to say n to the 3. No, it is under square root. So this is like n to the 3 over 2. So now, based on the fourth method, which was based on the degrees, what is the limit of this? Limit of numerator is 2. Limit of the denominator is 3 over 2 or 1.5. Limit of this sequence is infinity, because the degree of numerator is bigger than the degree of denominator. So immediately we say limit n approaches infinity of this sequence is infinity. Again, because the degree of this is 2, the degree of denominator is 3 over 2. So the degree of the top is bigger than the bottom, so infinity. Why it is positive infinity? This coefficient is positive, here is 1, so everything is positive, so it makes sense that the limit is infinity, not negative infinity. But if we had, let's say, negative 4 here, then the limit is negative infinity. The other way that you can find this limit is to use the first method. What was the first method? Keeping the dominant terms in numerator and denominator. In that method, we have n2 over radical n3. We ignore this. Then we have limit n2 over n to the 3 over 2. Because here we have a division, we subtract the powers. 2 minus 3 over 2, 2 minus 3 over 2 would be 1/2. So we have limit of radical n when n approaches infinity. N to the 1/2 is radical n. And limit of radical n when n approaches infinity is infinity, because radical infinity is also infinity. A square root of infinity is infinity. And it's the same answer. The other way for finding limit of this sequence is using L'Hopital, but using L'Hopital is not really a good idea, because you have to take derivative of radical n to the 3 plus 4n, then you get another radical. It makes it so complicated, and it's possible that you cannot find the answer at all. So it's not a good idea to use L'Hopital, at least for this question. And the other way is to divide numerator and denominator by highest degree of denominator. If you want to use that way, don't forget, the highest degree of denominator is radical n to the 3, or n to the 3 over 2. Now look at this example, cosine of n pi over n plus 4. You should not be confused by cosine. Notice the inside of the bracket. It's very simple expression, n pi over n plus 4. And we know that how to find limit of n pi over n plus 4. We know 4 different methods for finding limit of the inside of the bracket. For example, if we just keep the dominant terms, n pi over n would be pi. So the limit of inside of the bracket is pi. Another way, the degree of numerator is the same as denominator, so we just keep the ratio of the coefficient pi over 1. So as you can see, there are different ways to find the limit of the inside of the bracket. And just after we find the limit of the inside, just take cosine from that, and that's the answer of this limit. Let me show you. So for finding limit of this sequence, limit n approaches infinity, of cosine of n pi over n plus 4, for finding this limit, because we have no n here, we move limit to the inside. We focus basically on the inside. You don't need to write it this way, but it's good to write it this way. So we say for finding this limit, we focus on the inside. So we focus on limit of n pi over n plus 4. Now, what is the limit of n pi over n plus 4? For finding this limit, you can use L'Hopital rule. You can use all the methods that we have learned so far. Limit of this expression is simply pi. For example, if you want to use the dominant term method, this is the dominant term, this is the dominant term, n pi over n is pi. This is one method. If you want to use L'Hopital rule for this, you can say limit of pi x, or x pi, the order really doesn't matter, over x plus 4 when x approaches infinity is, based on the L'Hopital, we take derivative of the top, pi. What is the derivative of the bottom? 1. So it's pi. This is another way, which is based on the L'Hopital method. The other way, if you remember, the degree method. We look at the degree. The degree of the top is 1, because we have n to the 1. Degree of the bottom is n to the 1. When the degree is the same, the limit is a number. What is that number? The ratio. The ratio of what? Ratio of coefficient of n over coefficient of n. Here coefficient is 1. Here coefficient of n is pi. Pi over 1 or pi. Another way, divide every term of the numerator and every term of denominator by n. So you divide this by n, divide this by n, divide this by n, simplify, and you can get same answer. Cosine of pi is, what is cosine of pi? -1. Because remember unit circle, pi is here, and the cosine at pi is -1. Because cosine is x-axis. What is x value at this point? -1. What is sine of pi? 0, because the y value of this point is 0, but the cosine is -1. Now look at this example. I highly recommend you pause the video here, try this example by yourself, and then continue watching the video. The given sequence is e to the power of -2n over n to the 2 plus 1. Don't confuse yourself with exponential function. Focus on the exponent, because in the exponent we have n. E is just a constant. Focus on the exponent. You have -2n over n to the 2 plus 1. What is the limit of -2n over n to the 2 plus 1? the degree of numerator is less than the degree of denominator. When the degree of numerator is less than the degree of denominator, based on the fourth method that we have learned, the limit of this is 0. So, for finding the limit of e to the power of negative 2n over n to the 2 plus 1, when n approaches infinity, we focus at numerator. We focus at exponent, not numerator. We focus at the exponent. And we can bring limit to here because exponential function is a continuous function, so we can do this. Look at this. We have negative 2n over n to the 2 plus 1. In different ways, you can find this limit. If you want to use the fourth method, in the fourth method, we look at the degree. The degree of the top is 1. The degree of the bottom is 2. When the degree of the top is less than the bottom, the limit is 0. So this is e to the 0, and then the answer is 1. This is one way for finding this limit. If you want to use method 1, what was method 1 again? Method 1 was the method that was based on keeping the dominant term. What is the dominant term in the numerator? Negative 2n. In the bottom, we have n to the 2. Negative 2n over n to the 2 is negative 2 over n. And limit of this is 0 because we have a number over infinity. So this approaches 0. So based on this method also we get e to the 0, which is 1. You can use also L'Hopital for finding the limit of this. If you write negative 2x over x to the 2 plus 1, then if you apply L'Hopital, when x approaches infinity, then you would have negative 2 over 2x, and this is obviously 0. And this is the third method, or L'Hopital method. So with the L'Hopital method also, we get e to the 0, 1. L'Hopital method. What about dividing every term of the top and every term of the bottom by highest degree of the bottom? Let me show you that method here because it takes to do. I cannot do it here. So we have e to the negative 2n over n to the 2, n to the 2 over n to the 2 plus 1 over n to the 2. This is 1. This is negative 2 over n. When n approaches infinity, this is 0. This is 0. And because numerator is 0, 0 over 1, because in the denominator we have this 1, all of this is 0. So we have e to the 0, and e to the 0 is 1. Now look at this example. This is the first example that in the equation of the sequence, we have exponential function. We have 2 to the n and 5 to the negative n. For finding limit of this sequence, it's a good idea. First, rewrite the given equation in the form of 2 to the n over 5 to the n. We prefer to have fraction for finding limit of sequences. Because the power of 5 is negative, we move it to the denominator and we make the power positive. So we want to find limit of 2 to the n over 5 to the n when n approaches infinity. For finding this limit, attention, we don't have several terms in numerator, several terms in the denominator. We have only a single term in numerator and a single term in the denominator. If we had several terms in numerator and several terms in the denominator, we can just keep, similar to the previous questions, just the dominant terms. But here we have only a single term. Now we have to think about this. Which one of these two functions in numerator and denominator, 2 to the n and 5 to the n, are bigger terms when n approaches infinity? It should be clear for you that when n approaches infinity, 5 to the infinity is significantly bigger than 2 to the n. And because the denominator goes to infinity faster, our first guess at least is that this limit should be 0. And our reason is this, because the denominator goes to infinity. Both of these are exponential, so they grow very fast. But which one between these two goes to infinity faster? Definitely 5 to the n. Because in 5 to the n, you multiply 5 by itself. So it becomes larger and larger, faster than 2 to the n. So the limit should be 0. But if we want to give a proof for this, we can do it this way. We can say, we can write this limit in the form of 2 over 5 to the n. So we combine these two and we write it this way. We make the powers the same. 2 to the n over 5 to the n is the same as 2 over 5 all to the n. Now, this is clear that this limit is 0. Because, attention, if I name this number, whatever is in the bracket, as r, this ratio is less than 1. And when we have a number less than 1 and it raises to the power of infinity, the limit is 0. You should know this fact, that limit of r to the n when n approaches infinity is 0 if r is less than 1. And of course bigger than 0. If we have a number like 1/2, 1/3, 2 over 5, numbers like that, if these numbers raise to the power of infinity, the limit is 0. And the reason is this, because if we multiply 2 over 5 by 2 over 5 and times by 2 over 5 forever, this becomes a smaller and a smaller and a smaller and a smaller, and it goes to 0. Because if infinitely times we multiply 2 over 5 by itself. The other reason is to look at the graph of y equals r to the x, which r is less than 1 and bigger than 0. The graph of this exponential function is something like this. And as you can see, when we go to the right, far to the right, when x goes to infinity, attention, this is x-axis. If we go far to the right, the graph of this function, as you can see, approaches to x-axis. It gets closer and closer to x-axis. So, by looking at the graph of r to the x, which r can be 1/2, 2/3, any number like that, the graph goes to 0. As you can see, this distance between the graph and the x-axis gets smaller and smaller as we go to the right. So, this limit is 0. Look at this sequence. 3 to the n over 5 to the n plus 7. Here the story is a little different. We have two terms in the denominator, 7 and 5 to the n. Based on the method that we started this video, you can immediately ignore this because you know that this is significant term. We can ignore this, and then we have 3 to the n over 5 to the n. The denominator again is bigger, so this approaches 0. This is a fast way to find the limit of this sequence. But if we want to prove this, we can write it this way. We have limit n approaches to infinity, 3 to the n over 5 to the n plus 7. If you want to get to the result very fast, you can ignore 7. Then we have 3 to the n over 5 to the n, and this is like 3 over 5 to the n. And because again the base is less than 1, 3 over 5 to the n when n approaches infinity is 0. But if you want a better solution, a more mathematical way, remember the method that was based on dividing numerator and denominator by highest degree of denominator. Here we don't have highest degree, but we have the highest term, which is this. So we divide the numerator and denominator by 5 to the n. So basically we have this. So we divide every term in numerator, every single term, and the denominator by 5 to the n, and we have this. Now look at these things that here we have. The limit of this is 0 because the numerator is 3 to the n, the denominator is 5 to the n. We can write this as 3 over 5 to the n. Let me write it in the form of 3 over 5 to the n. 5 to the n over 5 to the n is 1 plus 7 over 5 to the n. N goes to infinity. We know that this limit is 0. In denominator we have 1 plus 7, which is a number over 5 to the infinity is 0. Any number over infinity is 0, so the limit is 0. The other way that you can find the limit of this sequence is to use L'Hopital. And basically, to use L'Hopital, you have to write this in the form of 3 to the x over 5 to the x plus 7. By taking L'Hopital, by applying L'Hopital, derivative of 7 would be 0. Then you are going to be left with these things, and then you can find the limit. But these methods that I showed you here are easier than using L'Hopital for finding limit of this sequence. We use L'Hopital whenever other methods that are simpler, they don't work. Why we have to use L'Hopital for this question? So using L'Hopital is not a good idea for finding limit of this sequence. What about this? N times e to the negative n. This is completely different story. Attention, in this sequence we have exponential and we have n, which is basically like a polynomial. So we have two types of functions here, exponential and n to the 1. Definitely the best thing that you can do at the beginning is to rewrite this in the form of n over e to the n, because it's easier to work with a fraction when we try to find a limit. If it is possible, write it in the form of a fraction. Now, what type of limit we have? If you pay attention, when n goes to infinity, this is infinity. This is also infinity. And infinity over infinity is indeterminate form. And we have only a single term in numerator, a single term in denominator. If we had several terms in numerator, we ignore smaller terms. But here we have a single term in numerator, a single term in the denominator. The thing is that we have to be able to figure out which one is bigger, the infinity at the numerator or infinity at the denominator. Which one is dominant? If the numerator is bigger, then this goes to infinity. If the denominator is bigger, then the denominator is bigger, then this converges to 0. So we have to figure out what is the limit of. We have to find the limit of n over e to the n when n goes to infinity. For finding this limit, because these two functions, these two expressions basically, are different types, it's not easy to compare them. So what method do you think is good to use for finding this limit? We can use L'Hopital. We write this in the form of x over e to the x. We replace n with x. Then we apply L'Hopital. Based on L'Hopital rule, for finding a limit like this, we take derivative of the top and derivative of the bottom. Derivative of x is 1. Derivative of e to the x is e to the x. Now what is this limit? 1 over e to the infinity. 1 over infinity is 0. So this sequence converges to 0. What we can conclude from this? The limit is 0, so this converges to 0. This shows that between numerator and denominator, which one is bigger? Denominator, because the limit is 0. So this means that the denominator is significantly, infinitely bigger than this. So it means that n, which is in the numerator, compared to e to the n, which is in the denominator, is basically nothing, because the limit is 0. Let me tell you an important fact that is good to memorize. Not only the limit of n over e to the n is 0, limit of n to any power, n to the power of 2, n to the power of 10, n to the power of 1 billion, over e to the n, when n goes to infinity, is 0. P here is a real number. P can be 1, 2, 3, 5, and so on. And even negative numbers. So for any value of p, limit of n to the p over e to the n, n goes to infinity is 0. Again, let me explain to you what is the meaning of this. From this, you have to keep this in your head. Exponential functions like e to the n are significantly bigger than the polynomial functions. Let me show you examples how we can use this fact, which I have written here, for yourself to find limit of sequences in 1 second. For example, suppose you want to find the limit of this sequence, n to the 2 minus 4n plus 7 all over, for example, e to the n. This is a polynomial like n to the p, n to the 2, n to the 1. This is like a polynomial. In the denominator we have exponential. We know that exponential is significantly bigger. So what is the limit of this sequence without any solution? If just we want to find the answer of this limit, if we want to know what is the limit of this sequence at infinity, the limit is 0. What about this? an equals n to the power of 100 plus, for example, 2000 all over, let's say, 3 to the n. Again, in numerator we have just a polynomial. In denominator we have exponential function. Maybe you ask yourself, but this was e to the n. E is a number 2.7. It doesn't matter, it is e to the n or 2 to the n or 3 to the n or 5 to the n, as long as the base is a number greater than 1, like 2, 3, 2.5, 1.4, 7, 10, and other positive numbers greater than 1, the limit is 0. So this sequence converges to 0. And attention, what if this expression was flipped? This was in numerator, the polynomial was in the denominator. What about that? Because the limit of this is 0, if we flip this, the answer should be flipped. What is the reciprocal of 0? Infinity. So if the exponential is in numerator and the polynomial is in the denominator, then the sequence is not convergent and it is basically divergent. Let me show you an example here. Let me erase here to show you an example of that. For example, suppose we have this sequence. an is given 3 to the n plus, for example, 1 over n to the 4 minus 5 n to the 2 plus 7. And you want to know what is the limit of this sequence. Immediately you have to say this sequence is divergent. It's not convergent at all, because the numerator has exponential function. And exponential functions grow faster than polynomials. This is significantly bigger than this. So this goes to infinity. And because it goes to infinity, it is divergent. So this example was very important, and this result here is also very helpful for you to keep this in your head. Now look at this example. Can you tell me what is the limit of this sequence when n goes to infinity? Right away, without any solution. In numerator we have a polynomial, n to the 2. It can be n to the 2 plus something else, but it's just n to the 2. And in denominator we have 3 to the n, which is exponential. So what is the limit of this sequence? Yes, it converges to 0. As you can see, this is a really important result. But if you want to give a proof for that, if you want to show a solution for this, you can prove it with L'Hopital method. You have to write it in the form of limit of x to the 2 over 3 to the x as x goes to infinity. Then we apply L'Hopital rule, and based on L'Hopital we have to take derivative of the top and derivative of the bottom. Remember, derivative of b to the x is b to the x ln of b. So derivative of 3 to the x is 3 to the x ln of 3. This is just a derivative rule that you have to know for doing this question. But when we apply L'Hopital rule, still we have infinity over infinity, because still we have x in the top and in the bottom, and x is infinity. So What we have to do? We have to apply L'Hopital rule again. What is the derivative of the top? 2. Derivative of the bottom? Attention, this is a coefficient, so keep it aside. Focus on this. What is the derivative of 3 to the x? 3 to the x ln of 3. But we had this coefficient here, so multiply by the coefficient. You don't need to use product rule at all. Ln of 3 is a number. Leave the number, take the derivative of the actual function. The function is 3 to the x, the derivative of 3 to the x is 3 to the x times ln of 3, and we multiply by ln of 3, which we had before. Now, what is this limit? 0. Why this limit is 0? Because in numerator we have a number, in denominator we have x, in the exponent 3 to the infinity. 3 to the infinity is infinity, 2 over infinity is approaching 0. So this sequence here is convergent to 0. And let me mention this. If we had this sequence, what about this? 3 to the n over n to the 2. This is exactly reciprocal of this. So this goes to infinity. Because here numerator is significantly bigger than this. And again, for proving this, it's easy. Do the same thing as I did here. Simply flip these expressions from numerator and denominator. So this given sequence here is infinity, and this one is divergent. Now look at this example. Here we have a logarithmic function, ln of n over n. Again, we have a new type of function, logarithmic functions. Do you remember from previous examples that exponential functions grow very, very fast compared to polynomials? Ln or logarithmic functions are inverse of exponential function. Exponential functions grow very fast. So, what happens to ln? Logarithmic functions, they are inverse. So, if they grow very fast to infinity, so logarithmic function ln of n, they grow to infinity but very slowly. So, we know that this goes to infinity. This also goes to infinity. N goes to infinity, these go to infinity. But which one is going to infinity faster? N, because ln is the inverse of exponential functions. Exponential functions grow very fast. So, logarithmic function grow very slowly. If you remember graph of ln, ln of x, look at the graph. When x goes to infinity, the y value also goes to infinity. This becomes larger and larger, but it goes to infinity. This goes up, this curve goes up very slowly, as you can see. For example, suppose here is 1 million or something like that. ln of 1 million is very small number. So this means that this function goes to infinity very slowly. So without doing anything, we can claim that probably the limit of this sequence should be 0. But to prove this claim, we have to show our work. We have to give a proof. And the best proof is L'Hopital again. Because this fraction and this limit is basically infinity over infinity. When x goes to infinity, this is infinity. Ln of infinity is also infinity. So we use L'Hopital rule. We take derivative of the top, we take derivative of the bottom. Derivative of ln of x is 1 over x. Derivative of x is 1. X goes to infinity. 1 over x. X goes to infinity is 0. So the limit is 0. As we expected. And let me generalize this again for you as a formula, as a thing that you can keep in your head. Limit of ln of n over not only n to any power. But here p is positive. Like n to the 1/2, n to the 2, n to the 1/3, n to the 2/5, n to the 10, 20, whatever. This limit is always 0. Which means that ln goes to infinity very, very slowly. And even something like radical n, which is n to the 1/2, is bigger than that, because radical n is like n to the 1/2. Now look at this example. This example is very important in the limit of sequences. The sequence is n times by sine of 1 over n. Note that if we want to find limit of n approaches infinity of n times by sine of 1 over n, this limit is in the form of infinity times by 0. When n approaches infinity, this goes to infinity. 1 over n approaches to 0, and sine of 0 is 0. So this limit is in the form of infinity times 0. And infinity times 0 is indeterminate form. Don't make this mistake to think that infinity times 0 is 0. Attention, this 0 is something that approaches to 0. So this is not a real 0. So because this is not a real 0 times infinity, it's not going to be necessarily 0. It can be 0, but maybe it's not 0. So what method we can use for finding this limit? One way to find this limit is L'Hopital rule. Remember, L'Hopital rule is very powerful method that we know for finding limits. But maybe you think, how we can use L'Hopital? We use L'Hopital when we have fraction, but here we don't have any fraction. You are right. But attention, we can write this in the form of sine of 1 over n all over n to the negative 1. We move this simple term to the denominator and we write this as n to the negative 1. By doing this, now we have fraction. Numerator is sine of 1 over n and denominator is n to the negative 1. For finding this limit, we want to use L'Hopital rule. We have to take derivative of numerator and derivative of denominator. Derivative of denominator is simply negative 1 n to the negative 2. We bring the power down, we subtract the power by 1, and this is the derivative of denominator. What is the derivative of numerator? Derivative of sine is cosine of 1 over n times by derivative of inside. But if you pay attention, this inside is basically n to the negative 1. So derivative of the inside is derivative of this. And derivative of this is simply negative 1 n to the negative 2. So derivative of sine of 1 over n is this. And it's not bad idea to put a bracket for all of this. Now if you pay attention, this completely cancels with this. What remains? After doing L'Hopital, we have limit of cosine of 1 over n, n approaches infinity. Limit of 1 over n when n approaches infinity is 0, and cosine of 0 is 1. So this limit equals 1. This sequence is convergent sequence and it converges 1. The other way that you can use for finding this limit is to rewrite this limit again in the form of sine of 1 over n over 1 over n. Attention, 1 over n is n to the negative 1. But now I prefer to write it in the form of 1 over n. Now let me remind you something from limit of trigonometric functions, which is this important relation. Limit of sine of x over x when x approaches 0 is 1. If you remember this relation, we can use this relation for this limit that here we have. But maybe you think by yourself, but this is n approaches infinity, but this was about 0. Yes, you are right, but attention. Limit of sine of x over x when whatever is here approaches 0. Now look at these expressions here. 1 over n and 1 over n when n approaches infinity. These things, these expressions approach to 0. So because these expressions approach 0, so based on this rule, this limit is equal to 1. From L'Hopital method also we got same answer. So we can use this rule, and based on this rule, this limit is 1. But if you prefer to write this and prove this, that For finding this limit, we can use this relation. Let me show you how you can do that. Please pay attention. I am going to name this expression in the bracket. I am going to do basically like a substitution. I am going to name this u, for example. So this limit is limit of sine of u over u. N approaches infinity. If n approaches infinity, 1 over n, which is u, so attention, u is 1 over n. If n approaches infinity, u approaches to what? Because u is 1 over n, so then u approaches to 0. So we want to find limit of sine of u over u when u approaches 0. Now you can see that this is exactly this. And based on this rule, this limit is equal to 1. Now look at this example. The sequence 1 plus 1 over n to the power of n. What is the limit of this sequence? Limit of 1 plus 1 over n to the power of n as n approaches infinity. Let me remind you from limit of functions that limit of 1 over 1 plus x to the power of x when x approaches infinity is e. And basically this limit is same thing, and so the limit is e. But here we want to give you a proof for this. But if you remember this from limit of functions, this is very famous expression, and limit of this expression as x approaches infinity is e. But here I want to give you a proof for this. Before we start, let me tell you something about this limit. When n approaches infinity, what is the limit of the bracket? When n approaches infinity, 1 plus 1 over n is approaching 1. Because n approaches infinity, this approaches 0, so 1 plus 0 is 1, and the power is infinity. Here, many students, many people may think that, okay, 1 to any power is 1. We know this fact. Yes, you are right, 1 to any power is 1. But the thing that you have to notice here is that this is not really 1. We write 1 here for the limit, which means that this expression is approaching 1. As you can see, this is not really 1. This is 1 plus 1 over n. Because 1 over n is approaching to 0, we say, okay, this is 1. So 1 to the infinity is indeterminate form. Is one of the most important indeterminate forms in limits. So 1 to infinity is not necessarily 1. It can be 1 in many examples, but we will see in a moment that in this example the answer is not 1. The answer can be 1, this answer can be e, the answer can be 2, the answer can be infinity, and other numbers. And so we have to find the limit. For finding this limit, I want to define a function. Basically, the idea is that I want to use L'Hopital rule at the end of the story. First, I define this as a function, 1 plus 1 over x to the x. The reason that I define this function is that I want to use L'Hopital rule. And you know that for using L'Hopital rule, you should not work with n. You should rewrite the expression in terms of x. Because when the variable is n is integer, and taking the derivative of an integer is a mistake in mathematics. So we rewrite this in the form of x, and we name this expression y. You can name it whatever you want. I prefer to name it y. Now, we take ln from this y. There is a good reason for that, you will see. If we take ln, then we have ln of 1 plus 1 over x to the x. Because we take ln, x goes to here based on the property of logarithmic function. We can write x times ln of 1 plus 1 over x. If you wonder why we take ln from both sides of this relation and we get to here, because at least now it seems that this is a little more complicated than this. But the thing is that we want to bring this exponent down For that reason, we take ln, because with the aim of the ln, with the property of ln, we can bring the exponent down. Now all the variables are here. We don't have any variable in the exponent. That's the reason behind taking ln. Now we try to find the limit of this expression when x goes to infinity, not n, x goes to infinity. Then after we got the result of the limit of this expression, then we say ln of y is this. So we can find y by solving for y. So now we want to find limit of this expression. Forget this, focus on this. We want to find limit of this expression when x approaches infinity. So this is the idea. We want to find limit of x times ln of 1 plus 1 over x as x approaches infinity. But if we want to use L'Hopital rule, you know that we need fraction. But we don't have any fraction. Easily, we move this to the denominator and we write it as x to the negative 1. We move x to the 1 to the denominator and we write this in the form of x to the negative 1. If we bring it back up, it's again x. Why we do this? Because we need fraction and we want to take derivative of numerator and derivative of denominator. Now we use L'Hopital rule. Derivative of denominator is negative 1 x to the negative 2. What about derivative of numerator? For numerator, remember derivative of ln. Derivative of ln an expression is 1 over that expression. Of course, we have to multiply it by derivative of the inside because of the chain rule. So, derivative of ln of 1 plus 1 over x is 1 over 1 plus 1 over x times by derivative of the inside. In the inside, as you can see, we have 1 over x. And attention, 1 over x is basically x to the negative 1. So, we have to take derivative of the inside, which is this. Derivative of this 1 is 0. What is the derivative of x to the negative 1? Derivative of x to the negative 1 is negative 1 x to the negative 2. So, derivative of ln is 1 over whatever is here times by derivative of inside, which is this. Now look at the numerator and denominator. You can see that this is common with this. We can cancel the common terms from numerator with denominator. And we have now to find the limit of this when x approaches infinity. When x approaches infinity, the limit of this part is 0. 1 over x, 1 over infinity is 0. So we have 1 over 1, which equals 1. So we prove that, please pay attention, we prove that the limit of, not y, the limit of ln of y, which is this, is 1. So now we have proved that, please pay attention, we have proved that ln of y approaches 1. If ln of y approaches 1, we can conclude that because of the continuity of ln, we can conclude that the y is approaching to the 1, not e to the negative. Because ln of y approaches 1, the y approaches e to the 1. Remember, when we want to solve ln of y equals a, the y would be e to the a. You should be familiar with solving this type of equations. We know this rule. So because ln of y approaches 1, the y approaches e to the 1. So this limit is e to the 1 or simply e. Now look at this example. The sequence is 1 plus negative 1 to the n. Probably right now you should be familiar with this sequence, negative 1 to the n. If you write the terms of this sequence, you would see that the terms are negative 1, then 1, negative 1, 1, and so on. They become 1, negative 1, negative 1, 1, and so on. So as you can see, these terms do not approach to a number. So this sequence is not convergent, and basically this is a divergent sequence. And the reason is that we have a negative 1, then 1, negative 1, 1, and they don't approach to a number. So this is a very famous example of a divergent sequence. If we want to write this in more mathematical way, -1 to the n, when n is even, is 1, because we know that -1 to any power which is even, like -1 to the 2, -1 to the 4, -1 to the 6, -1 to the 100, is always 1. When n is odd, like 1, 3, 5 and so on, the value of this sequence is -1. When n approaches infinity, we have odd numbers at infinity and even numbers. So this sequence can be 1 or -1. When we approach to infinity, we don't know the value because it goes to infinity. It can be even, odd, even, odd. So this sequence becomes 1, -1, 1, -1 and so on. So this sequence is divergent. Now let's see what we have about this given sequence here. 1 plus -1 to the n. The terms of this sequence are 0. Why the first term is 0? Because if we plug in 1 here, the value of this sequence is -1. -1 plus 1 is 0. So the first term of this sequence is 0. If we plug in 2 for n, the value of this is 1. 1 plus 1 is 2. So the next term of this sequence is 2. Again, we have 0, 2, 0, 2, and so on. As you can see, this sequence is also divergent because at infinity, we don't know which value we are going to get at the end. So this sequence is also divergent. And if you want to write this similar to here, when n is even, this equals 1. 1 plus 1 is 2. So the sequence is 2 whenever n is even. Whenever the index of the sequence, the number of the term, is odd, this sequence is 0. And at infinity, we can be odd or even. So we don't know to which value we approach. So the sequence is not convergent. And this is a divergent sequence. Now look at this example. Cosine of n pi over n. Before we start doing this question, let me remind you something about sine and cosine. It's good to know that. Sine of n pi is always 0. And the reason for that is the unit circle. If you remember the unit circle, sine of, for example, 1 pi is here. And sine of pi is 0. Sine of 2 pi is here, is also 0. 3 pi is again this point. Sine of 3 pi is also 0. Sine of 4 pi, sine of 5 pi, sine of 6 pi. So sine of n pi, which n is any integer, is always 0. And remember, sine is the y value of this point. The y value of this point and the y value of this point is 0. They both are on the x-axis. So sine of n pi is always 0. What about cosine? For cosine, the story is a little different. When n is 1, we are at this point. At this point, cosine is the x value. X value is -1. At this point, x is -1. At the other point, x is 1. So cosine of 1 pi is -1. But cosine of 2 pi is 1. Cosine of 3 pi, -1. Cosine of 4 pi, again 1. This should remind you a famous sequence. What is that sequence? What is the sequence that is -1, then 1, -1, 1, and so on? Yes, -1 to the n. So we have this important relation. Sine of n pi is always 0. But cosine of n pi is either -1 or 1. And you can find its value based on this formula. Cosine of n pi is exactly the same as -1 to the n. For example, let's check this. Cosine of 4 pi should be equal to -1 to the 4. Is this right? Yes, this is 1. This is also 1. Because 4 pi is basically here. And as you can see, its value is 1. Now let's back to this question. Immediately we write this in the form of -1 to the n over n. So basically here we want to find the limit of n approaches infinity of negative 1 to the n over n. What is this limit? 0. Let me give you my reason for that. Numerator is either 1 or negative 1, but the denominator approaches infinity. When you have a number over infinity, which that number doesn't go to infinity, it's just negative 1 or 1 divided by infinity, the answer is 0. So the limit of this sequence is 0. But if you want to give a better proof for this claim, you can do it this way. Let me show you a little better way for writing this. You can discuss about n is even or n is odd. When n is even, what happens to this? Negative 1 to the n, when n is even, it's like 1, so we have 1 over n. When n is odd, negative 1 to the n is like negative 1 over n. Now, we can say that when n approaches infinity, this approaches 0. In the other case also approaches 0. Because both of them approach to 0, now we can say that, we can conclude that the original sequence also approaches 0. This is another way for writing the solution. Now look at this example. Negative 1 to the n times n over n plus 4. Immediately we can write this as negative 1 to the n times by n over n plus 4. This should be familiar for you, and you should be able to find the limit of this part right away without thinking. The degree of the top is the same as the degree of the bottom, so n over n, 1. Yes, the limit of this part is 1. What about the other part? We know that this is either 1 or negative 1. But this part approaches 1. So what we can conclude about all of this? This part is divergent because it approaches 1 or negative 1. The other part approaches 1. And between them is multiplication. 1 times 1 is 1. 1 times the other one, which is negative 1, is negative 1. So this sequence approaches to 1 or negative 1. So we can conclude that this is divergent sequence. It's not a convergent sequence. Again, for writing this, we can say we consider two cases. N is even, n is odd. When n is even, what happens? This is 1. So we have n over n plus 4, because 1 times by this is same thing. When n is odd, this is negative 1. So negative 1 times that's negative 1 times by n over n plus 4. Let me write this. Negative n over n plus 4 in this form. This is negative 1 times n is this. Now, when n approaches infinity, what happens to each of these limits? Now, let's find limit of each of these. What is limit of this when n approaches infinity? And what is limit of this case when n approaches infinity? Limit of this one is 1. And limit of the other one is negative 1. Because n over n is 1. Negative n over n is also negative 1. We ignore 4. We have seen examples like this before. Now we can see that when n approaches infinity, this sequence, which is both of these, approaches to either 1 or negative 1. And because the answers of these two limits are different, they don't approach to a same number, they approach to different numbers. We conclude that limit of an when n approaches infinity does not exist, which means that this sequence is divergent. Now consider this sequence, sine n over n. We want to find limit of this sequence when n approaches infinity. Limit of sine n over n. Note that we cannot find this limit with the usual method, because when n approaches infinity, denominator is n, so it approaches infinity. But remember, sine of n, because n approaches infinity, sine of infinity does not exist. Because if you remember graph of sine, it oscillates up and down. It goes up, down. When we go toward infinity, when we go far to the right, this graph goes up and down forever. So when n approaches infinity, because sine of infinity does not exist, we cannot find this limit. We know that sine is between -1 and 1, but we don't know any value for that. And if you remember from the limit of functions like this, for finding such limits, we use a squeeze theorem or sandwich theorem. So for finding this limit, we use a squeeze or sandwich theorem. For that, we start with the trigonometric part. We start from sine or cosine, depending to the question. Remember that the sine or cosine functions are always between -1 and 1. We know this rule. Always, any sine or any cosine function are always between -1 and 1. Now, the idea is to convert this to sine n over n. So we have to change this to sine n over n. For doing that, we note that we need n in the denominator. So we have to divide left side, middle, and the right side of this inequality by n. If we divide everything by n here, then we have -1 over n sine n over n, and in the right side we have 1 over n. Now look at this. This complicated expression now is between two simple expressions. Now we want to find limit when n approaches infinity of the left side and the right side. What is limit of -1 over n when n approaches infinity? This limit is 0, because we have a number over infinity. Any number over infinity is 0. What is limit of the other side? That is also 0, because the limit of the left side is 0, limit of the right side is 0. So the limit of the middle term, the limit of this term, should also be 0, because it is trapped between these two. They go towards 0. And because this is between them, this should also go to 0. And this is basically based on the squeeze or sandwich theorem. So now we say from a squeeze theorem, we conclude that from a squeeze theorem, we can conclude that limit of sine n over n when n approaches infinity is 0. So this sequence approaches 0. Please pay attention. If you don't want to give a proof and just want to find the limit of this sequence, you don't need to write all of this. Let me show you why you can find this limit easily without the squeeze or sandwich theorem. This is a proof, but without a proof, how we can find this limit easily? Please pay attention. We have a fraction. The denominator of this fraction is n, and n approaches infinity. Numerator is sine of infinity, and sine of infinity does not exist. That's right. But we know that although this is something that this limit does not exist, but we know something about sine. We know something about cosine. What is that? We know that whatever it is between 1 and -1. If something is between -1 and 1 in numerator, we don't know the value, but it's between -1 and 1. Divided by infinity, it approaches what? It approaches 0, obviously. So you can find the limit. If you don't want to show your work and just you want to know the value of the limit of the sequence, in this way you can find easily the limit of the sequence. If you want to see more examples of a squeeze theorem or sandwich theorem for finding limit of sequences, watch my video for this topic. I have a full video about this topic. Here we have an example of a sequence with factorial in the formula of the sequence. Before we start this, let me remind you the definition of factorial. n factorial is n times n minus 1 times n minus 2 and so on up to 2 times 1. For example, 4 factorial is 4 times 3 times 2 times 1, which is basically 24. Look at this given sequence here, n minus 1 factorial over n factorial. Immediately we can write this in the form of n times n minus 1 based on definition of n factorial. N factorial is n times n minus 1 times n minus 2, and this goes up to 2 times 1. What about n minus 1 factorial? N minus 1 factorial starts from n minus 1, then we have n minus 2, then we have n minus 3, and so on. We continue this up to when we get to 2 times 1. Now look at the numerator and denominator. This cancels with this, this cancels with this, this cancels with this goes with this. What remains? 1 over n. So this given sequence is basically 1 over n. What is limit of 1 over n when n approaches infinity? It is 0. So this sequence is convergent and converges to 0. So the only thing that was necessary here is to simplify this, get to here, and then this limit is 0. It is obvious. But let me show you the better way for simplifying this expression, this sequence here. Let me erase this, because this way that I simplify this expression is not a very good way for simplifying this expression. Please pay attention. N factorial, which is in the denominator. Yes, n factorial is this. But is it really necessary to open n factorial in this way? No. The better way is to write n factorial is n times by, we want to write all of this here. But attention, what is this that you want to write here? N minus 1 times n minus 2 times n minus 3 up to 2, then 1. This expression is basically exactly n minus 1 factorial. So we don't need to open n factorial completely. We write n factorial is basically n times n minus 1 factorial. And if you wonder why it's good idea to stop here and don't open all the n factorial in this form, because we know that in numerator we have this expression. Why should I open the n factorial completely in this form? It's better to write it in this way, and then we keep n minus 1 factorial in numerator. This completely goes with this and we get 1 over n. This is the better way for doing this. I know the answer is the same, but this is the better way for writing your solution. And then we can say limit of 1 over n approaches infinity is 0, so this sequence converges to 0. If you want to learn more about factorials and working with factorials and simplifying expressions like this, if you want to learn more about these things, watch my video about factorials. Now look at this example, n times n factorial over n plus 1 factorial. Here we notice that in this sequence, the bigger factorial is in the denominator. We have n plus 1 factorial. So we are not going to touch the numerator. We leave the numerator as n times n factorial. We only open the denominator, which is n plus 1 factorial. What is n plus 1 factorial? It is basically n plus 1 times by n times by n minus 1 times by n minus 2. We go up to when we get 2 times 1. Always we start with this term, then the next term is same term but minus 1. N plus 1 minus 1, this goes with this, and then we have n. Then we subtract this term by 1, then we have n minus 1. Then we subtract another one, we have n minus 2, and so on. But should I open n plus 1 factorial this way? No. Here, the better way for opening n plus 1 factorial is to just write this n plus 1, and instead of opening all of this and writing all of these terms, what are all of these? If you remember definition of n factorial, this is exactly n factorial. And because in numerator also we have n factorial, so it's better to, instead of all of this, write just n factorial. Now this cancels with this, and we have n over n plus 1. What is limit of n over n plus 1? when n approaches infinity. It should be clear for you that this limit is 1. And the reason for that is that the coefficient of here is 1. 1 over 1 is 1. This is the dominant term in numerator, dominant term in denominator. N over n is 1. We have seen limits like this in this video a lot. So this sequence is convergent and converges to 1. Now look at this example. In numerator we have exponential function 5 to the n. In denominator we have n factorial. This is a little tricky question. Let me show you how we can find limit of this sequence. First of all, note that 5 to the n is 5 times by 5 times by 5 times by 5. How many times? N times, because it's 5 to the n. So we have n 5 in numerator that are going to be multiplied by each other. What is n factorial? N factorial is basically n times by n minus 1 times by n minus 2, and it goes up to when we have 2 and 1 at the end. Now I am going to separate each 5 over each of these terms. And attention, we have n terms, n5 in numerator, and exactly we have n bracket or n terms in the denominator. Because, for example, when we have 4 factorial, how many terms we have? 4 times 3 times 2 times 1, 4 term. 5 factorial, 5 term. N factorial, n term. So we can separate this in this way. We can write this in the form of 5 over n times 5 over n minus 1 times 5 over n minus 2, and this goes up to when we have 5 over 5, 5 over 4, 5 over 3, 5 over 2, and 5 over 1. Because attention, we want to find limit of this sequence when n approaches infinity. When n approaches infinity, so we have 1, 2, 3, 4, 5, 6, 7, and we have infinite terms in the bottom, infinite 5 in the numerator. So we can write this in this form. Now please notice, this is the tricky part of this question, and please attention to my explanation here. Focus on these terms. Keep these terms and these terms aside. Focus here. For these terms that here we have, numerator is smaller than denominator. For example, what is the term that here we have? 5 over 6. What is the term that here we have? 5 over 7, 5 over 8, 5 over n minus 2, and n minus 2 n approaches infinity, so this is bigger than numerator. So for all the terms that here we have, these terms, all of these terms that are here we have, they are smaller than 1. Why these fractions are all less than 1? Because their numerator is less than their denominator. For example, 5 over 6 is less than 1. 5 over 10 is less than 1. So all these terms are less than 1. So because these are less than 1, we can claim that all of these, attention, these are less than 1. And between these terms, we have multiplication. When something less than 1 multiplies by other thing, it makes that thing smaller. So we can claim that this sequence is less than equal 5 over n. We keep this term here, and we keep these terms because these are not smaller than 1. 5 over 5, 5 over 4, 5 over 3, 5 over 2 times 5 over 1. So far we have shown that this sequence is less than this. And let me mention something else here. Also, it should be clear for you that this is always greater than 0. So far we have shown that an, which is 5 to the n over n factorial, is greater than 0 because this is always positive, and less than equal to this. How many 5 in numerator we have? 5, 5. How many 5 we have in numerator? 5 to the 6. And in denominator we have n times by 5, 4, 3, 2, 1, which if you want you can write just 5 factorial. So far we have shown that this sequence is always less than equal 5 to the 6 over n times 5 factorial. Now I want to use a squeeze or sandwich theorem. Our idea is to find limit of this sequence, but because finding limit of this sequence is complicated, we are going to find the limit of the left side and limit of the right side. The left side is 0, and so its limit is also 0. But what is the limit of the right side? Limit of this expression, limit of 5 to the 6 over n times by 5 factorial when n approaches infinity is also 0. So limit of the right side is 0. The left side is always 0. This is 0, so its limit is also 0. Now from a squeeze theorem, we conclude that limit of 5 to the n over n factorial when n approaches infinity is 0, because this is squeezed between these two. When this is 0, the other side, limit of the other side is also 0, so the limit of the middle term should also be 0. So we prove that this given sequence here is convergent to 0. But I have to tell you something about this relation. Please pay attention. When we are writing this, we suppose, for writing this relation, we suppose n to be greater than or equal 6. Because when n is like 1, 2, 3, we don't have so many terms, so many 5s in numerator. If, for example, n is 1, do we have 5 times 5 times 5 times 5 times 5 in numerator? No, we have just one 5 in numerator. But because here our aim is to find limit at infinity, so we can suppose we have many 5s in numerator and many terms in denominator. So there should be no problem for writing this inequality. Now look at this example. N factorial over n to the n. For finding limit of this sequence, we use similar idea to the previous question. N factorial is n times n minus 1 times n minus 2 times 2 times 1. And n to the n is n times n. How many n's we have in denominator? N we have in denominator. If we separate numerator over denominator, we have n over n times n minus 1 over n times n minus 2 over n times by 1 over n. If you pay attention, the first fraction is equal to 1, but the next fraction is less than 1. The next one is less than 1. The term before this, which is 2 over n, basically we have 2 over n exactly. And because n approaches infinity, this is less than 1 as well. So because all of these terms are less than 1, so we can conclude that all of this is less than 1 over n. Let me explain this to you again. This is something less than. This is 1, but this is less than 1, less than 1, less than 1. When you multiply the terms that are less than 1 by something, it makes all of this less than this value. For example, suppose you have 4 here. If you multiply 4 by 0.5, then you make 4 a smaller number, which is 2. And so it makes sense to say that this is less than 4. If we write this here, it should make sense. So because all the terms before 1 over n are less than 1, so all of this is less than 1 over n. So we have proved that the given sequence, this sequence, is between 1 over n and of course greater than 0, because this is always positive, this is positive. Now again we want to use a squeeze theorem or sandwich theorem. What is the limit of this? Limit of 0 when n approaches infinity is 0. Limit of 1 over n when n approaches infinity is also 0. And from a squeeze theorem we conclude that the limit of the middle term, which is limit of an, limit of this sequence when n approaches infinity is also 0. And this is based on a squeeze theorem or sandwich theorem. When the limit of the left side and limit of the right side is something, the limit of the middle term is also same thing, because it is squeezed between those two other limits. So its limit should be the same. So again, for finding limit of this sequence, we use a squeeze or sandwich theorem. I hope by watching this video you have learned how to find limit of sequences. In this video I try to show you different examples, easy examples, hard examples from different topics. And I try to show you different methods, different ways for doing the questions. I try to show you different type of methods for doing this question. If you want to learn even more than this for finding limit of sequences, I have videos for each of these topics. For example, for L'Hopital, for using L'Hopital for finding limit of sequences, using a squeeze theorem for finding limit of sequences, and other topics. You can watch those videos if you want to see more examples. If you like this video, please subscribe to my channel and see you in the next videos.